Okay, so let's continue our discussion of Claisen condensations and look at some specific example problems. All right, in this first example, we want to predict the major product and then draw the mechanism for the reaction. So when I draw the products of a Claisen condensation, I actually do it sort of the opposite way or sort of flipped around than the way the textbook author does it. And so let me show how I think about drawing the products. So I sort of pattern it after the nucleophilic acyl substitution reactions. And so I think about, this as being my substrate. And so this is my electrophile. It's the one that's going to be attacked by the nucleophile, and it's going to lose the leaving group. And so I start by drawing this part of the molecule. And we're always going to get the beta keto ester. And so we're always going to have the alpha carbon, and then from what became the enolet and becomes our nucleophile, we're always going to get the ester part of the molecule. So the electrophile is going to give us this part that we have here. Then we're always going to have the alpha carbon, and then we're going to get the ester from the nucleophile. And then this is my alpha carbon, right? This is the alpha carbon of the what became the enolet and was the nucleophile. And so to finish off my product, whatever else is coming off the alpha carbon, that's going to be coming off the alpha carbon here. And so in this case, it's just a methyl group. And so that would be the product of this Claisen condensation. Now to draw the mechanism, what we're going to do is we're going to start by deprotonating the alpha carbon. And so this methoxide ion is going to steal the hydrogen. Those electrons will become a lone pair on the alpha carbon. All right, and now this thing is going to attack another one of the ester molecules. All right, now I'm sort of drawing mostly my product at this point. Here's the alpha carbon. And there's the ester. Right, so that's my alpha. On the carbon that was attacked, we're going to have the OR and the O minus coming off it. So that's what was the carbonyl carbon. That's the OR that's eventually going to pop off as a leaving group. And then I know from my product that also on the alpha carbon, I had that methyl group. All right, so then we're going to reform the carbon-oxygen double bond. And at the same time, we're going to expel that leaving group. All right, and then finally, well, I guess there are two more steps, right? Now, because we're in basic conditions, and this hydrogen is super acidic because the ion that's going to be formed is going to be stabilized by being able to spread the negative charge on both of those oxygen atoms, the strongly basic conditions are going to pop off that hydrogen. And give us this ion. Oops. Switch back to the pen here. All right, and then the last step, the acid workup, is going to give us a hydrogen to make the neutral molecule. I'm sorry, my pen is not working great, so that's why this H3O plus doesn't look great. But the lone pair steal those hydrogens, and that bond becomes a lone pair on the oxygen. And that's the mechanism for this Claisen condensation. Okay, here's another example. They're not asking us to draw the mechanism, we just want to predict the major product. And so again, I pattern this off of the nucleophilic acyl substitution reactions. And so if I imagine this as being my electrophile, right, this group is going to stay, but we're going to pop off this ethoxide as a leaving group. Not a great cyclopentane, but I'll live with it. Then, right, we get the alpha carbon, and then we're going to get the ester part of the molecule. And then, right, this is the alpha carbon. And so from the enolate, whatever else is coming off the alpha carbon, that's going to be down here. That's a little bit better cyclopentane. All right, so that's going to be the major product when this compound undergoes a Claisen condensation. All right, last example. So now we're going to look at the Dieckmann cyclization. So when we have an intramolecular Claisen condensation. And in this particular case, we're going to get two different products. And we want to draw both products. And the reason we're going to get two different products is because the molecule is not symmetrical. And so either this can be the alpha carbon that gets deprotonated and is the nucleophile that does the attacking, or this alpha carbon can be deprotonated and it can be the nucleophile that does the attacking. And so if we imagine these two products, let me draw these in two different colors. So what I like to do is I like to number the carbons. So if I imagine that starting with this one, if this is the alpha carbon that's doing the attacking, this is going to be the electrophilic center that it attacks. And so if I number the carbons that are going to be in that ring, I have 1, 2, 3, 4, 5, 6. And so I'm going to get a cyclohexane. And then I can just put these groups on the respective carbons. And we're going to lose, right, if this is the one that's the electrophile, this is going to come off as a leaving group. And so to draw my product, I know I'm going to have a cyclohexane, so I can just draw the cyclohexane. And then I can call any carbon number 1 that I want, and so I'll call that carbon 1. And then 2, 3, 4, 5, and 6. And now I just need to put what is coming off of each of these carbons. And so coming off carbon 1 is this ester group. Right, there's nothing off 2 and 3. 4 has a methyl. And then 6, right, this popped off as the leaving group. And then so 6 is just going to have the carbon-oxygen double bond. And so that's going to be one of my products. The other product is going to be if I deprotonate this alpha carbon, and it becomes the nucleophile that attacks this electrophilic center. So let's do a different color and number it that way. So if this is the alpha carbon, that's going to be 1, 2, 3, 4, 5, and 6. So again, I'm going to have a cyclohexane. right? And in this case, if this is the electrophilic center, right, this is going to pop off as a leaving group. And so coming off carbon 1, I have this ester group again. Let me number the carbons here. 1, 2, 5, and 6. Now in this case, carbon 2 has the methyl group. And nothing on 3, 4, and 5. And carbon 6 again has the carbon double bonded to the oxygen. And so these would be my two products. And so it's this methyl group that makes this molecule not symmetric. And so I get two different products instead of one. And the difference is just where that methyl group is on the ring relative to the carbon double bond to the oxygen and the ester group.